All right, good afternoon, everyone. So today we're going to finish up our discussion of backpropagation, and then we'll move on to how we implement this all in Python using something called PyTorch. So last time we derived this, this page of stuff. Looks kind of complicated. Let me erase some of this to make room for what we'll talk about next. So, so here we have our two-layer neural network, inputs, hidden layer scores, activations, hidden layer outputs, cost, and then we have our first layer parameters, second layer parameters, and our training labels. And so this is with a batch size of B. And so all these curly braces mean we have sets of these features over the different batch elements, hidden score vectors over the different batch elements, and so on. And we use the multivariable chain rule to derive. So, okay, we started with our forward pass, and then we said for the backward pass, what we can do is we can use the multivariable chain rule to derive a number of relationships we can reuse over and over to make this all very efficient. So we worked our way from right to left, and we derived these different gradients, and we used one to derive the next, and so on. And then finally, we got the partial derivatives with respect to our different parameters in these equations here. And so that was, in some sense, a lot of work to get there. The next thing to do is to rewrite these equations in terms of vectors and matrices, because as we know, it's not very practical to implement things using summations and so on. If we can get everything into vectors and matrices, that will be more efficient, but also it will make these expressions look a lot nicer, I think in some sense make a lot more sense. So that's our objective next. And that's what we have on this next page. So the very first thing is to figure out how we're going to write our matrix quantities. And so we're going to try to be as faithful to everything we've done in the course since Unit 2. So let's first take a look at X, which is, as always, our matrix of training features. So the way that we always have written X is as you go down the rows, you get the different training samples. And we always use I for the training samples. So that's what we're going to do here. So the different rows of this matrix are the different training samples. Now, we're working with a mini batch, not full data set. So we have a total of B different rows because we have B items in our mini batch. And then when you look across X, you should see the different features in the data set. So for this particular demo that we've been looking at, there's only 2, but in general, you could have D features. And to connect this with the quantities that we have been working with, let's say on the previous page, you can see that each one of these is the vector of different features for the ith training sample, or ith batch element. So we essentially need to pack these things together into our matrix. So this is how we're going to do it. So there's a transpose here because each one of these guys is a column vector, and we're stacking those column vectors together into a matrix. But then after we've done that, you can see that we're really indexing I over those columns, but really we want to index I over the rows. So we finally need to add this transpose so that I is going down the rows. Okay, is that making sense? How we're taking these column vectors, each one is for a given batch element, and then we're transposing it just to be consistent with how we've written things all semester. Any questions on that? Yeah.
This is the vector per batch, right?
So yeah, so these samples are all the feature vectors in a batch. Yeah. In one batch, yes. And then essentially, we're going to do the same procedure for all the different quantities that we have. So we have here, we have like these label vectors for the ith batch element, and we're going to construct our Y matrix in the same way. We take each of those vectors, stack them across the batch, and then transpose them so that we have I going down the rows of the Y matrix. Same thing with the hidden score vectors. Each one of these is a column, but we have one per batch element, so we stack those into a matrix, transpose it, so that as we go down here, we again have I. Same thing with the output score vectors. And okay, we'll talk about the, let's see. No, I guess it's going to be the same thing again for the activations. So this is not the A matrix we saw in Unit 2, which was the ones with the X's. This is completely different. This is a matrix of activations, which are these things, the outputs of our sigmoid in the case of the demo. All right. Okay, so we've established the different matrices that we're going to be working with. And so now we have to figure out how we can translate. Let's say we start with the, let's start with the forward pass. How do we translate this into the matrix quantities? Okay, let's start with the first equation. So remember that this is a column vector. And here we have a matrix times a column vector and a column vector. And that's for a single batch element I. So what I want to do is I want to put this together for all the different B vectors in my batch. So the way to do that is just to stack the columns from left to right. So I'm going to have this, and next to it I'm going to stack the next one, and next to it I'm going to stack the next one until I have a total of B of them. And then I'll have everything in my batch. So that works out. So if I do that here with the different i's, then I also want to do it with the different xi's. Right? And so this WH is just going to be multiplying against all the columns in that X matrix. Or actually, okay, so the first point is I'm going to stack things. I'm going to stack things from left to right. But now, how do we relate that back to the Z matrix we defined earlier? So what I said is these guys, you can imagine them stacked like this with I going this way. How do I write that in terms of the Z matrix on the previous page? That would be this one. So here's that stacking left to right, but notice that the Z matrix involves the transpose, right? So I don't want that transpose here. So if I transpose both sides of this equation, that means it will get rid of this and it will put the transpose over here. So on the previous page where I have this, that's actually going to be my ZH transpose. That's where we get this. Okay, so this is going to be ZH transpose. Okay. And then what about when I do this over here with the x's? Again, I'm stacking I this way, which is the transpose of how I've defined the X matrix, where I was stacked down the rows. So it's the same situation here. We don't want the transpose, so we put it there. And that is the quantity we have over here. Okay, so this is going to be X transpose is this. Is everybody with me so far? Any questions? Okay. The last thing is, what about this BH? So this is going to be a vector. And what we want to do is, as we stack these things left to right, these columns are changing because they're the different batch elements. But what about this? As I stack this left to right, is it going to be different or the same, or what's going to happen? Same, right? So I'm going to have the identical thing repeated. What's a way that I can write that with a vector matrix product, or matrix product if you want? How can I what can I do to copy this into a matrix?
Identity.
No, identity would not work because identity doesn't have the right dimensions. Because BH has a single column, so I have to multiply it by something else that has a single row. Identity wouldn't work. Vector ones, exactly. So if I take this guy and do an outer product with the vector ones, that's just going to essentially copy it over and over. Okay, so that's what we're doing here. We have a 1 transpose, which means it's a row vector, and this one is going to be of length b, which will make this overall matrix have b columns. All right, so that's how we translated that first line in the forward pass into a matrix expression. Yeah.
Could you repeat how many columns B has? B is a matrix, or like that quantity?
No, just B is the batch size.
I meant like little b.
Oh, this guy? Okay, so this guy has to match the dimension of the hidden, right? These have to match in dimension.
Okay.
So however many hidden units you choose, in the demo we had 4, that will be how many bias terms you need to have.
Okay, thanks.
Yeah. All right, so is everybody good with this first line? All right. So for the next one, if I wanted to do exactly the same procedure, we could do that. We could stack these AHs this way with the I this way. And then because we defined the A matrix the same as the Z and X matrices, that would be AH transpose if we did that. This would turn into ZH transpose. And so we could write this if we wanted AH transpose is this activation function times ZH transpose. So that would be like writing it like this. And that's fine. But the thing about this activation function is that it acts element-wise on every one of the components. So I could write it with the transposes, or I could write it without the transposes. It's going to do the same thing. It's just going to apply the sigmoid to every one of the elements of this matrix and return a new matrix. Okay, so I'll just write optional on these transposes. You can put them in or you can leave them out. I mean, they either both need to be there or they both need to not be there. But otherwise, it's optional. Originally, I left them out just because it's a little cleaner without them. All right. Okay, any questions on the next line? Okay, third line is essentially the same as the first, except for the H's being replaced with O's, X's with A's, but otherwise it has exactly the same form. So it's going to look like this. And the last line, can't really simplify it too much. Yeah, I can't really simplify it too much because the way the loss is defined, it has to operate on vectors. You can't really stick matrices in there without redefining it, so we're just going to leave that the same. Okay, so we got through the forward pass. Everybody good with that? Okay, so the next thing is how to write some of these gradient expressions. So we have this one, and so we see that this is dj dzo ik, and this is just the ith row and kth entry of the capital ZO matrix. Right. So one way to write this as in matrix form would be I write this entire matrix, dj dzo, the entire matrix, and then I'm just going to extract out the ith row and kth column. So that's just another way of writing this. Let's see, could I? All right. And on the right side, I can't really do too much to change it. Again, I have to just leave it like this because the J is defined to operate on vectors, and even though I have a matrix, can't really stick the matrix in there. So I'm just going to leave the right side as it is. So we're done with that. For the next one, we can again think of this as the ith row and lth column of some matrix. And here you can see I have another ith row, kth column of another matrix, and then kth row, lth column of another matrix. So, and as you can see, or maybe as you can guess, there's going to be a matrix multiply here. So I have one matrix here that's going to be some matrix multiply of two other matrices. Okay, so one is going to be the AH matrix, the ZO matrix, and the WO matrix. The only thing we have to figure out is whether we need to insert some transposes to get all the indices to align. So let's just first think about the quantity on the left. So the way that it's written here, I is going down the rows, L is going across the columns. So I'll just put these little arrows in here to remind us of that. Now, when I look at the next term, this quantity has I going down the rows, which is great because that's exactly what we want to have happen on the left side of the equation. And then we have K going across the columns, which is great because that's what we want. We want the sum to be the inner multiply of the matrix multiplication. And so if we're lucky, going down this way, we'll also have K. That way we won't need to do any transposes. And sure enough, we do. Here's K. So this is K is going down this way. And then finally, L is going across the columns. And that's great because we know that going across the columns here, that needs to match going across the columns here. So we have L in both cases. So it's great. We have basically the AH matrix equals the ZO matrix times the WO matrix. Simple as that. So we have DJ DAH, that matrix, times DJ DZO, that matrix times WO. Okay, so is that making sense? Or so this is essentially the procedure we need to go through for all these terms. In some cases, we might need to stick in some transposes to make things work, but it's basically the same logic. Oh, except for this term. This term is different, as we'll see in a moment. All right. Are there any questions about how we converted this to matrices? Or is that pretty good? Good? Okay. Okay, so the next one is pretty different. So when we look at the indices, we have IL here, we have IL here, and we have IL here. So is that a matrix multiply in the classic sense of multiplying two matrices? Or yeah, well, okay, we have to be careful what we mean by dot product, because dot product often means inner product. And actually in Python, the DOT operator is a matrix multiply, so we don't want to do that. We don't want to call it that. It's what we call an element-wise multiply. So we have a matrix here, we have another matrix here, and we're just multiplying first times first, and that's going to give us the first term here. And we multiply second times second, and that's going to give us the second one here, and so on. So it's just an element-wise multiply of those two matrices. The notation that I have seen most often used for that is this circled dot. And officially it's called the Hadamard product. That's what this element-wise thing is here. So that's what we're going to do. We're going to form matrices for those three terms, like this, and then just put the dot there to tell us, or circled dot, to tell us that that's our Hadamard product. Yeah, and in MATLAB, it is a dot asterisk, but in Python, it's actually just the asterisk itself. If you do asterisk with two matrices, it just assumes it's an element-wise multiplication. It does this. Okay, so that's this next step here. All right, so IL. All right, any questions on that? Okay, and I didn't mention it, but this operator H prime, this is just an element-wise operator, so this is just going to apply that derivative, to every element in that matrix. So we're just writing it this way. Okay, good. So ready to move on? Okay, next one is this one. So here we have a vector on the left, not a matrix, right? Just one index k. And then we have a matrix indexed by ik. And here you could say, well, if we want to write this as a matrix times something to do the sum, we want this to be a row vector, and that will give us, sorry, column vector, and that will give us a column vector. So here the thing is that we want the column vector on the left. Let's just say we want k to come down that way. Now we notice that on the right, these are switched. They're not how we would like. So, but if we transpose this quantity, then we will have, so maybe I'll put a transpose there. After transposing, I will be coming across this way. K will be coming across that way. And that's nice because that k aligns with this k. And this I is what we want for our sum here. And then we just need I to be going down this way. So we're going to have a vector of ones. We can think of, as you go down that vector of ones, there's going to be index of I. And so essentially we just need to make sure that we transpose this ZO matrix. So that's where we get dj do dzo transpose times our b-dimensional ones vector, and that will give us dj dbo, which is going to be a column vector. Okay, any questions on this one? All right. Okay, the one below it has exactly the same form. So everything I said applies. It just, we have the hidden outputs instead of the hidden scores instead of the output scores. And the very last thing we have to figure out is this one here. Okay, so here we can say, if I leave the left side as is, we have k going down the rows, L going across the columns. And we would like this guy to have k coming down here and I going across the columns. But we can see to have that happen, we just need to transpose it. So let me put in the transpose here, after which I is going this way, k is going this way, which is great. And then the last thing we have to figure out is, do we need to transpose this? And the answer is no, because I is coming down the rows and L is going across the columns. Finally verify that L is going across the columns of both left and right side. Great, everything's matching up. So we basically just need to transpose this and then leave this matrix as is. And that's what we have here. This part is transposed, and then this is just the matrix as is. Okay, so that's it. And now we have everything written forward pass in terms of matrices, backward pass in terms of matrices. And now it's an efficient implementation. And also just, I think it's nicer to look at than the previous page with all the million indices and summations and stuff. Okay. All right. Is everybody okay with everything so far? Any questions on anything? All right. So this is just a summary, essentially, of what we have. So our whole goal, the reason we're doing all this is we want to compute gradients of these parameters so that we can run gradient descent to minimize our likelihood. And so we finally have this overall scheme. We call it backpropagation to compute these gradients. And first it has a forward pass, which essentially initializes all the variables and computes the cost. And then the backward pass uses all those variables that we initialized to compute the gradients. So that's essentially it. The very last thing to point out is I promised that I would discuss a little bit like what is this term? I said it depends on how you define J. So here's just a couple examples. And we've actually seen these equations before back in Unit 5 maybe, or 6, or both. So let's say that this is binary cross entropy. In that case, we only need one output from our last layer. It's just going to be the score, a real number. And so we have the way we define our loss in this case, when we have 0, 1 labels, we derived it back in Unit 5 to be that. And so now essentially that is the J function that we need to take the partial derivative with respect to the output score. And you can see that's not too difficult. Just by the chain rule, you take the derivative of this, that gives you 1 over this. And then you take the derivative of the inside with respect to ZO, and that gives you this. And then this one, take the derivative of this respect to ZO, you just get minus y. So this is what is the missing piece that we need to know how to execute that line, and also this line, there's the cost. And what if it's k-ary cross entropy loss? So in that case, the way we handle that is we one-hot code our y labels. So we make a vector of dimension k. And in fact, we build the linear layer at the output of the network to output k different scores. So we have an output dimension of k. And our training labels, we're one-hot coding them so that if the y sample is in class little k, that means that our y vector for that same I, that same trained sample, will be all zeros, except we'll have a 1 in the kth entry. So that's the one-hot coding. So with the y's now defined to be vectors instead of, or the ith training sample defined as a vector instead of an integer, we can rewrite our cross entropy loss like this. I think this is some stuff we derived back in Unit 5. So here's our one-hot coded labels. And all we need to do is take the derivative of this with respect to the ZOIK. And again, that's not too difficult. It's very similar to above. We get this. So, so that kind of concludes all the details of the forward and backward passes of backpropagation. Okay. Any last questions on that? Okay. So, as you can see, it's kind of an involved procedure, right? And if you were working on this stuff 10 years ago, you would have had, or someone in your research group would have had to code this manually. You know, for your particular network architecture, you would have had to code all this. But fortunately, since about 2015, there are software packages out there that do this kind of amazing thing called automatic differentiation, which essentially implements the backpropagation algorithm automatically under the hood from you so that you don't have to worry about any of those details. You set up your model, you tell it to optimize that model, and then under the hood it figures out how to do all that backpropagation and does it for you. So that's what these different frameworks are. There's a number of, these are some of the most popular ones. I actually updated this. I didn't get a chance to put it in the notes, but if this I think was from like last year or something, but there's another one called JAX that is really cool. It's popular today. And there's one other one, I can't remember what it is, but the ones that are the most famous today would be TensorFlow, PyTorch, Keras, and JAX. And we are going to use PyTorch. I'll explain why in a moment. In some sense, it's the most friendly one, so that's why we're going to use it. But as you can see, there's different ones. Some of them are kind of proprietary. I think Amazon uses, I can't remember if Amazon uses MXNet. I think, so it depends where you work. So TensorFlow is out of Google. So if you would go to work at Google, you'd probably be using TensorFlow. Facebook made PyTorch. So if you're working at Facebook, you'd definitely be using PyTorch, and so on. So it kind of depends where you work. I don't know what Uber uses. But anyway, so just a little bit of history and comparison. So TensorFlow was the first of these, released in 2015. Because it's now 8 years old, it's very mature, very widespread. The original version was kind of cumbersome, difficult to use. There's a version 2 that's a little bit better, but from everything I've heard, it's still not as easy as the other options like PyTorch. But again, depending on where you work, you may have to use TensorFlow. Okay, so then Keras is, you could say, is kind of like a wrapper that can sit on top of TensorFlow or Theano or CNTK, which are some other frameworks. I'm not sure if they're not even in the top ones anymore, but they used to be at some point. So what Keras does is it just wraps TensorFlow and it makes it super simple, but it actually hides a lot of stuff. And if there's a bug, sometimes it can be really tough to figure out what's going on because everything is hidden from you. And if you want to do something very standard, like just code a classification network or something, you can do it in a matter of like 1 or 2 lines, which is great. But if you want to do something a little different, it may be very difficult or impossible to do this with Keras. So, there are some machine learning courses that teach things in Keras, but the problem is it doesn't really teach you how to really work with a more complex system, which you might need to do, especially if you're doing research or something like that. So PyTorch is something that offers full, it's completely general, like TensorFlow. It was proposed a bit later, so they were able to think about things a little bit more clearly and to propose a model that's just a bit easier to use, but just as powerful. And this one has grown to be by far the most popular in the research or academic communities. So maybe not industry. Maybe industry would be still using TensorFlow, or maybe it's half and half now. I don't know, because it changes every month, every year. But we're going to use PyTorch. There's a few articles, they're a couple years old now, but these are articles that were comparing PyTorch and TensorFlow and Keras. But anyway, that's kind of high-level view of how these different frameworks relate. So now we're going to start learning a bit about how PyTorch does stuff. So it's a little bit involved, as you'll see. There's to fully train and apply a network, there's 5 different steps we're going to take. Each step has a particular way of doing things, particular objects that you have to create in PyTorch. And there's some really great tutorials if you want to learn more, or if you find these slides are not enough, or these demos in the course are not enough for you. Great tutorials there that lead you through it in a more detailed framework. Okay, so what I'm going to show you now is essentially the demo code to compute that 2-layer neural network with the blue things in the middle, green things on the outside. Just how did we code that? And that just is a pretty simple example of how you can create and train a simple neural network, 2-layer neural network. So the very first thing we have to do is we have to construct the data set we're going to be using and something called the data loader object. So the first thing to talk about is the data types. So as we know, when we work in NumPy, we work with ND arrays, which have a lot of features in them. It's not just like a data container. It's a structure that if you do if you have an ND array and you do like .t, it's a function that transposes it, right? It has all these other things under the hood there for you. Torch tensors are very similar. It's just PyTorch's version of the ND array that has a lot of those same things like transpose and dot and all that stuff. But it also has extra stuff that PyTorch needs for its automatic gradient or differentiation stuff. So it has more than an ND array, and there's straightforward ways to go back and forth. So if you start with a NumPy array and you just do torch tensor, then that will sort of take that data and it will wrap it to the torch tensor framework. And now these are variables we can use directly with PyTorch. And when we want to come back and print these things with matplotlib, you can't print the PyTorch tensors. You actually have to convert them back to NumPy. We'll show you how to do that in a moment. Okay, so now that we have our features and labels coded as torch tensors, we have to tell PyTorch about them. And so we create a data set, which as you can see here, a quote-unquote tensor data set. So we put it through this, and then that puts in all these other hooks and stuff that puts it in a framework that PyTorch wants to work with. And then there's one other thing, as we know, using mini batches is key for deep learning. So if you combine that data set with a few more hooks and abilities, you can do this. You can create what's called a data loader. And this data loader, for example, knows about how to batch things out. And so if eventually, this is what we'll eventually be doing, we'll eventually have a for loop, an inner loop, over every epoch, where in each epoch we need to take out our different batches, right? And we'll be able to do this like this. So this is just the for loop. So this loader, which is this thing we created, every time we call it, it outputs this data object, which has a batch of features and the corresponding batch of labels. So PyTorch is doing all the batching for us. And in fact, this data loader can handle the batching over multiple processors and stuff. So if you have a whole bunch of processors you want to use, it can know about that. It can abstract all that stuff away so that you don't have to worry about any of those details. So anyway, that's how we construct the data. And so now that we have like batches of stuff, we can work with them. We can compute gradients and all that stuff. All right, so this is the very first step. Any questions so far? Yes.
How do we choose the batch size? Is there like a rule of thumb or something?
That's a great question. It's what we call a hyperparameter. It's one of the many things we need to choose, and there's a bit of intuition sometimes. It also is depending on how much memory your system has, and it is also a matter of trial and error and tuning. So we'll talk about that a little bit later. Okay, so here we're just choosing 100. But it's a great question. You could try other things and see how they work. Okay, so now we have our data set, but we need to construct the neural network that we're using. So for this, we're going to use Torch's NN library, NN being neural network. And so we're going to create things using that object-oriented sort of style. So we're going to create a module or an object, and it's going to have, as we saw before, there's an initialization block. So when you instantiate this thing, when you call net to create an instantiation of it, it's going to go through this code here. And this code is going to take in these inputs, which is the number of inputs, the number of hidden layer quantities, and the number of outputs. And so here you can see when we finally call it, we're going to tell it use nx, which in the demo is 2, nh, which in the demo is 4, and because we're doing binary classification, nout will be 1. So now what happens in the initialization is we're going to build the different blocks within our network. So like nn.sigmoid, so this library knows about sigmoid activations, so we're going to say make something called an activation out of a sigmoid, make our first dense layer out of a linear layer. So this is PyTorch's version of the linear layer that has weights and biases. And you have to tell it now the dimensions. This is going to have nn inputs and nh outputs. So that's going to be our so-called dense 1 layer. And the second one is going to be nh inputs, because those are our activations, giving finally nout outputs. That's going to be our second dense layer. So now we have the building blocks. And then here we define the forward pass, where we just connect the building blocks into the network that we want. So we start with x being the input to the network. And you can see x goes through the first dense layer. Then it goes through the activation, the sigmoid. And we just redefine it as x. And then that second x goes through the second dense layer. It goes through the output activation, which in this demo is also a sigmoid, and finally gives us our output. So we tell it the forward pass, and it is smart enough to do the backward pass later using automatic differentiation. Okay, so here's the instantiation. All right, so that's how we construct the network. Any questions there? Okay. Next, we have to tell it which optimizer, which algorithm to run. So, for example, stochastic gradient descent, the one we learned about, that's the most basic one. It is an option, but there's much more. People have built on that, and they've added all these fancy things to it, like momentum, which is, I think, something you saw in the lab for Unit 6 at the very bottom. Extra credit section was incorporating momentum. There's also various adaptive step size sort of things. There's all this sophisticated stuff people have developed. So there's many algorithms that are somewhat known and famous. So this is like a short list: rprop, RMSprop, AdaDelta, AdaGrad, Atom, and so on. And PyTorch has many of these for you to try. The one that most people use as just the first thing to try is the Atom algorithm. So that's one we're going to use here. And so we're going to do optim.atom. And now we need to tell that algorithm, first of all, what parameters are you optimizing? So for that, we tell it use model.parameters. So model was the thing we built here. And when we do model.parameters, it knows, okay, there's weights and biases here, weights and biases here, no tunable parameters in this activation, and so on. But it knows what the parameters are, and now our optimizer knows what parameters it's going to be optimizing. We also have to tell it any other things, like we're going to use a learning rate of 0.01. You could, depending on the optimizer, you could tell it to use particular kind of momentum and so on. So, and so we've now instantiated that into our opt object. So that's the optimizer. What about the loss? So we said that for our network, because it's a binary classification problem, we want to use binary cross entropy loss. So this is one of many loss functions that PyTorch knows about. There's also cross entropy loss, which is one that you could use if you have more than 2 classes. If you're doing regression, you could use MSE loss, which is just basically RSS. Or if you want to do something a little bit more robust to outliers, you could use L1 loss, which is essentially like the Laplacian loss that was on the midterm, the additive Laplacian noise model. So those are various options. We're going to use binary cross entropy loss for the task that we're solving. Now you can actually scale and combine these PyTorch losses. So if you want to do lasso, you could do like MSE loss plus some lambda times L1 loss. So you can do algebra with these losses. That works fine. All right, so we're kind of building step by step. We have our network, we have our data set, we have our optimizer, we have the loss. Now we have to put everything together. So this is where it gets more complicated. So essentially what we have here is we have an outer loop over the epochs. We're going to use 2,000 epochs. So remember, an epoch is going through all of our training samples once, and then new epoch, we shuffle those training samples to get out new sets of mini batches. So that's outer loop over epochs. Inner loop is for each epoch, we go through all the batches, one batch at a time, and that's the stuff, one batch at a time. So some of what we're doing in the beginning is just kind of setting up some arrays that will measure the loss over, the loss we're trying to minimize. We're gonna record the loss for every epoch, just so that we can print it out and see, is this thing decreasing? Does it need more epochs to decrease more? We'll also plot out or store the average accuracy so that we can see what's the accuracy over epochs. But let's take a look at what's happening in the inner loop, because that's the most interesting. So we saw the first 2 lines before. So this is where we take that data loader object and we call it, and it outputs data, which has the batch of features and the corresponding labels from the batch. Now there's all these little things that you have to do sometime in PyTorch just to get the data how it wants it. So this X batch for us is going to be a matrix, right, of B times B by 2, because there's 2 features, X1 and X2 in the demo. Y batch is just going to be a one-dimensional quantity of just the 0, 1 labels. But it turns out that PyTorch doesn't like that these have different dimensions. It doesn't like that this is a matrix and this is a vector. So we have to force ybatch to be a matrix itself, a matrix with just one column or one row. And we can do that with this. Dot view, that means just basically change change how you're looking at this data in some sense. And this means the very last dimension to be 1 rather than 0, for example. And this will change that that vector into a matrix. Change it from a list of numbers to a matrix with one row or one column, however you want to think about it. Does that make sense? So if you, what?
After dot reshape, you use.
Yeah, right. So reshape might be that reshape is, I can't remember, sometimes there's different ways to do things. Certainly reshape works in NumPy. It might be that view is the only thing that works for Torch, or it might be that you could also do reshape. I can't remember, but view is definitely one thing that works here. So now we have the data in a format that this likes. Another thing too, sometimes when you're working with classification, sometimes it wants that the ybatch are floating point numbers. The labels are floating point rather than integers. So that's another thing you have to watch out for sometimes. And if you don't, then you start to get these errors and it's complaining about something and you're like, what's wrong? Everything looks right. It's just it wants things to be in a slightly different format. So read the error messages closely to try to figure out what exactly is it complaining about. Is it complaining about the sizes of things? Then it could be oh, I need to make this into a matrix. Or is it complaining about the types? Then it's oh, maybe it doesn't like it to be a float or it doesn't like it to be an integer or something like that. Okay, so now we got our data ready. So now essentially we're going to do the forward pass. We're going to take our XBatch and we're going to put it through our neural network to get our outputs. And it not only did it compute the actual values of the output, but it actually learned this whole sort of sequence of operations that it's going to use for backpropagation. It kind of built this so-called processing graph, and it can actually use that to do its backpropagation in a moment. So that's sort of the forward pass. Now we're going to tell this is the criteria we set up, which is the binary cross entropy. We have to tell it, okay, what are the z quantities in this case, and what are the training labels? So these are the training labels in our batch, and these are the outputs of our model z, right? In this particular BCE, it's written in terms of the z's, which are real numbers, rather than the soft outputs, which go between 0 and 1. Okay, so this criteria now, this is how we compute our loss. We put in our z's, we put in our training labels, we compute the loss. And just for accounting purposes, we're going to append the batch loss to this empty array. And that way, if we want to see within a single epoch, how did the loss change over the batches, we can look at that vector. This other vector up here that we initialized, this is the loss once per epoch. So it doesn't tell us what happened within an epoch, it's just across epochs. Okay, all right, so we have our loss computed. And so now here's kind of the interesting stuff. In preparation for the backward pass, you want to tell the optimizer to 0 its gradient, because otherwise it will just add on to the previous gradient. So this is just how it's set up. So you tell the optimizer to 0 its gradient, and now you do a backward pass just by simply doing loss.backward. And the loss, because it's based on this output, and the output is based on the model, knows about the model structure, it knows that whole computation graph, and it can do all those complicated gradients and stuff that we derived. And so now all that stuff is sort of stored internally. All those gradients are computed, they're stored internally. And now to do one step, one gradient descent or whatever step, you just do opt.step. And it knows about the gradients that were computed here, and it takes that step. So if you're doing atom, it's not just a simple gradient, it's a bunch of other stuff is going on, but in principle, if you're doing just SGD, it would just be a simple gradient step. That's all that happens here. Okay, any questions so far? Yeah.
So we did loss dot backward, but could you also just do out dot backward? I mean, is the information?
No, I mean it's set up to do it this way.
Okay.
There's all this crazy complicated software under the hood,
Okay.
and it wants because see the out doesn't know the cost, right? It doesn't know the loss you're trying to minimize. So
Okay.
right, because it's like you have your output, but then that thing needs to go into a negative log likelihood or something. That's the thing you're actually minimizing. So that is something that you take the output, and then you add that information here at the criterion. So this is what you're really trying to minimize. Yeah.
Can you explain again this very line you had loss, the comparison between its loss?
Oh, this one. Yeah.
The out.
So this is sort of like in the mathematics we call this J ZO I, or let's just say J ZO Y. So this would be over our batch. These are our training labels, and these are our outputs. And then J was the binary cross entropy. So that's exactly what is being computed here. So if you want to see what the loss is, it's actually that number. But this is a data structure that contains more than just the number. It contains information about how to do the backward pass. But if you want to get out just the number, you do dot item. And that gets you just the number, and then that number we can store in this array. Yeah. So, okay, so we're almost done. So we've taken this gradient step, and now if we want to make a hard decision, just to evaluate our classification accuracy, you can just do out.round. So any torch tensor, you can round it to the nearest integer. That will be our guess, you could say our y hat, if you will. And then to compute the number of errors, you look at the difference between the guess and the training label. So, and then you take the absolute value. So basically, if they match, you'll get 0. If one is 0 and the other is 1, you'll get either a plus or minus 1 here, but then you'll take the absolute value, so that will be 1 for the error. And you just sum these across the batch. And this is how many errors you got within the batch. And so we're actually accumulating this. And so this is something that we initialize to 0 at the beginning of the epoch. And as we go through the epoch for every batch, we're just adding to it, counting how many errors we made across all the batches in the epoch. And when we're all done, if you want to plot the accuracy, you can do number of errors divided by the total number of samples in that epoch, total number of data samples, and you can turn that into an accuracy between 1 and 100. And then we can store like the average batch loss across all the batches. We can store that once per epoch. We can store this accuracy once per epoch, and so on. Okay, so that's sort of the hard part is to kind of get this stuff right for PyTorch. But typically what you do is you start with some example that works and you modify it. So you don't have to build this from scratch. So you have access to all these demos. You can use this as a starting point. Okay, any questions on this? All right. So let's just look at what happened now for our demo. We look over the 2000 epochs, and we're looking at the loss here. You can see the loss started out pretty high. It went very quickly decreased, but then it took kind of a little bit longer. And finally, you can see why we're letting it run for 2000 epochs, because it seems like it's finally settling down at that point. We can also look at the training accuracy, and we can notice that the training accuracy took a giant leap up to about 70%. Then it hung out there for a while, and then it started going up, and eventually got, close to 90%. And it seems like this is more or less stabilized after 2000 epochs, so that might be a good time to stop it. Okay. So now there's a few other little things to know, like how do we create this plot? So let me just kind of quickly say one of the things we had to do is we had to create sort of a new data set, if you will. And what we did is this is for every x0, x1 dot on a very dense grid of 100 by 100. So that would be 10,000 different x0, x1 pairs. We made a new data set called xplots that had 10,000 data points. And we basically just put xplot through, where do we do this? We put xplot, we first, of course, had to make it into a torch tensor because we constructed it with NumPy. We put it through a model, and that gave us our output activations. And then here is where we do converting them back into NumPy. You do dot detach, and then you tell it what format dot NumPy. And eventually to plot it, you have to reshape it and so on, but it's not very complicated. So eventually, that's how we constructed this heat map of the red stuff with the standard matplotlib stuff. Imshow. Imshow is the main plotting command we use here. Okay. Another thing we did is we made these little pictures that showed the value of the 4 different activations as a function of x0 and x1. So here, for this is the same very dense grid that we created with 10,000 points. But this is sort of like looking halfway through our network. So to do that, we can take that xplot tensor, we can put that through the model.dense one. So now it just puts it through that first linear layer. We put the result of that through model.activation, and now we've reconstructed the hidden nodes at the in the middle of our network. We've just sort of done this manually, and that's essentially how we extracted the stuff for this plot. The other thing to notice is that in the titles, we're plotting the weights that we learned. These are the different output layer weights, the 4 of them. So how do you get out the trained weights out of the model? You use this state dictionary stuff. So you do model.state dictionary. That makes a data structure that contains all the weights and biases of the model. And then you can pick them out one by one, like state dictionary dense 2.weight, that will get you your WO, and state dictionary dense 2.bias, that gives you your BO. And then we just plotted them in the title. Okay, so that's, I think we're almost done. Just, so we then took the same approach, used exactly the same code for the MNIST digit classification. The only thing we changed is we changed the number of hidden nodes to 100 from 4. We changed the number of output nodes from 1 to 10 because we have 10 classes. But we're still using the sigmoid activations, same loss function, same optimizer. Sorry. We're going to use all 50,000 training samples. And what's pretty cool is that with this simple 2-layer neural network, we got up to 97% accuracy, which, if you remember, is the same we got with the SVM. But I think the SVM, I can't remember which one takes longer to train, but certainly this one, once it's trained, is super fast to execute. You just push the data through that simple 2-layer network and you know what your labels are. The SVM, to actually use it, once it's trained, is you have to know all the support vectors, and you have to use all those support vectors to compute any test sample, any test label. So it ends up being a lot more expensive. And then finally, just to answer an earlier question, generally speaking, the hard thing about neural networks is there's a lot of parameters to tweak. There's a lot of choices to make. So we call this fine-tuning. And so here's, just for this network, the things we would have to choose. We have to choose the number of hidden units, right? We used 4 in the first demo. We talked about how probably 3 would work, 2 wouldn't. Probably more than 4 would work okay. For MNIST, we had to take it up to 100, but there's a question about whether that's optimal. Maybe a different number would have been better. We can choose the hidden layer activation functions. Do we use sigmoids? Do we use hyperbolic tangents? Do we use ReLUs? What do we use? There's all sorts of choices you can make there. You might wonder which optimizer. Most people use Atom, but sometimes people will say some other one will work. the learning rate, super important. And in fact, we'll talk later about how sometimes you want to start with a high learning rate and then make it small as you go through the iterations. The batch size is also another thing. The choice of batch size and learning rate must be made together, as we talked about. With smaller batches, you typically want to use a smaller learning rate to sort of average things out. And the number of epochs we saw, you generally can choose that by looking at how the curves evolve. And there's other options. You can use L2 regularization. That sometimes helps. And what's interesting is that is actually implemented as part of the optimizer using the weight decay option. So you just say weight decay equals like 0.1, and then it will add to the loss 0.1 times the 2 norm squared of your weights. So that's how you do it. And the very last thing is there's essentially 2 different ways to go about fine tuning. One is you, as a clever human, sit in front of a computer and you try things over and over again, and you build intuition and you make little tests, and eventually you narrow down and you get a design you're happy with. The other way is you can say, I have all this massive processing power and I just want some computer to go through all this massive number of combinations of things that, designs, and figure out for me the best one. And there's smart ways to do that where it doesn't just consider like every possible thing. It tries random things and then it focuses on the random things that work better. And so probably the most popular package to do that is called Optuna. So essentially for Optuna, you just tell it like, consider this list of possible hidden units, consider this list of activation functions, this list of optimizers, this list of learning rates, and so on. You tell it like all the things you want it to try, and you let it run, maybe for days, maybe for weeks, maybe for months, and you see how well it could do. So these are options for you for your projects. What I have seen in previous semesters is that they work about the same. Students are able to, by manually tweaking, are able to get about the same performance as Optuna. And Optuna, but again, Optuna is also something you have to use it in a smart way. You have to tell it, smart choices for the ranges of things to look at. If you're not smart about that, it's going to be too constrained and it won't find a good solution. So there's a bit of an art to doing both. Both are reasonable. Both, if you have the budget, you should try both in your projects. But there's no magic bullet here. So that's it for today. Thank you. Sorry I went over. And we'll continue with Unit 9, Deep Networks, on Friday. See you guys then.